In order to fix using Starsights, we need the azimuth of the star, which requires the observer's latitude, LHA of the star, and declination of the star to calculate, as well as the intercept of the star, which requires the true zenith distance and calculated zenith distance to calculate. To find the azimuth, the observer's latitude is as per the DR position, which does not require any calculation. However, the LHA of the star needs to be calculated using various figures from the nautical almanac. First, GHA Aries needs to be found, with any increment for minutes and seconds to be added. Let's assume that GHA Aries is 145 degrees for the hour and increment is 5 degrees. That gives us a GHA Aries of 150 degrees. Taking this to be the Earth, where the dot represents the North Pole and the line represents the Greenwich meridian, it should be noted that our angles are to be measured westwards. This means that Aries is positioned 150 degrees westwards from Greenwich. Next, we need to find the GHA of the star, which can be found by adding the sidereal hour angle of the star to GHA Aries, which gives us a GHA star of 210 degrees. The longitude is then applied to GHA star to find LHA star. Longitude is to be added if east and subtracted if west. Assuming longitude is 103 degrees east and added to GHA star of 210 degrees, the resultant LHA would be 313 degrees. The last piece of information needed to find the azimuth of the star is the declination. Taking this to be the Earth, where the line represents the equator, declination refers to the elevation of the star using the equator as reference, in either a northerly or southerly direction. This example shows the declination of the star to be 15 degrees north. Using the three pieces of information found, the azimuth can then be calculated using the ABC method. Through the use of a calculator, A equals sine latitude over sine LHA, where A is named same as the latitude if LHA is between 90 degrees to 270 degrees, or named different from latitude if LHA is less than 90 degrees or more than 270 degrees. B equals to sine declination over tangent LHA and is always named the same as declination. C equals A plus minus B and is named depending on whether A or B is greater. After C is found, it can then be applied to the following formula. Tangent azimuth equals 1 over cosine latitude times C. This will then give us the value of the azimuth. Next, we need to find intercept using the sextant altitude of the star. Before we use the sextant, we first need to establish the index error of the sextant. If index error is on the arc, the error is subtracted and added if the error is off the arc. The following diagram shows how a sextant altitude is the angle subtended at the observer's position by the star and the visible horizon. Assuming sextant altitude to be 45 degrees and index error to be 0.1 minutes off the arc, the observed altitude would be 45 degrees and 0.1 minutes. Height of eye correction, known as dip, then needs to be applied to the observed altitude in order to find the apparent altitude. Dip is always subtracted from the observed altitude. Assuming a height of eye of 8 meters, a dip of 5 minutes then needs to be applied. Total correction, which corrects for parallax error, refraction of the atmosphere, and other factors, then needs to be applied to the apparent altitude to find true altitude. Total correction is always subtracted. This gives us a resultant true altitude of 44 degrees, 54.1 minutes. From true altitude, true zenith distance then needs to be determined. Since true altitude plus true zenith distance is always 90 degrees, this gives us a true zenith distance of 45 degrees, 5.9 minutes. Next, we need to find the calculated zenith distance, which can be found using the following formula. Let's assume that the calculated zenith distance is 45 degrees. The difference between the true zenith distance and calculated zenith distance then gives us the intercept, which can be away or towards the azimuth of the star, depending on whether TZD or CZD is greater. Using the rule true tiny towards, this gives us an intercept of 5.9 miles away. When fixing using stars, we need two primary pieces of information, the intercept and the azimuth. Let's assume that the azimuth is 123 degrees true and the intercept is 5.9 miles away. This means that an intercept needs to be drawn 5.9 miles away from the azimuth of the star. A perpendicular line then needs to be drawn at the intercept point. This represents a position line of the ship. If a navigator were to make use of one or two more such position lines, the position of the ship can then be fixed.